We're going to make one together. And then if we have time, we're going to do a lab another day where we're going to make one. Or you guys are going to make one. Okay, so there's that. This one. Good morning, Louisa. I may turn this way so you guys can see the demo. Yeah, that's going to work. Okay, so, yeah, you're going to see that. Okay, Feeney won't be here, right? Okay, so somebody can move up. That's probably the best thing because Feeney won't be here today. So somebody can move up to that spot. Thank you, Errol. And yeah, Ellie, and one of you can move over here if you want to be closer. I just want to make sure you guys are close enough to see what's going on today for the demo. And Louisa, let's see, somebody else there too? Say hi if there's somebody else there as well. Okay, so here's what's up, phones away. Let's go ahead and draw mathematically what we're going to do, and then we're going to do it together to make a buffer together. If we have time, we'll do a lab another day. You making a buffer, but for now we're going to do one together. I'll tell you our chemicals. We've got acetic acid, and the formula is on the board. In German, it's Essig Säure because it's in acid or vinegar. That's this stuff. Okay, it's 1 molar. And then I got some solid sodium acetate. And you might remember from when you memorized the ions, the acetate ion is that big long one, okay? Why do I need both of those for my buffer? Each one provides what? What's one providing, what's the other providing, so to speak? Chelsea? Good, so there's my weak acid. Why? Because it's not one of the strong ones that you memorized, right? And this other one is, I only need to care about this, don't I? The Na plus is a spectator, so I don't need to worry about it. So I need that, and that's my conjugate base. Just so we're using the vocabulary, right? Okay, so let's figure it out. I'd like to make 100 milliliters of this buffer. Do I want to make 100? What did I decide last night? No. No, I decided differently. Let's make, what did I put in here? Let's make 20 milliliters of buffer. Is that what I want? I might have screwed up with this last night. No, that's going to be 10. 10 milliliters. So I want 10. No, I probably want a few more than 10. Phooey. All right. It doesn't matter. Okay. Let's make 20 milliliters. Sorry about that. 100. I don't make 100 because it's too much. All right. I don't want to waste the chemical because we don't have that much of some of this stuff. Okay. So let's figure out what we're doing. I got a solid, right? And I got a solution. The solid won't be much, and we can assume that the solid is not really going to change the volume. You know what I mean? Like adding a pinch of salt to some soup. It's not really changing the volume much. But we got to figure out what volume we want. Okay, so actually we got the volume. We could just take 20 milliliters. So we're going to do what? We're going to take 20 milliliters of our acid. HCH3COO. And let me do that now. Just a splash more. Okay, and I'm going to hold that there for a sec. Okay, there's my chalk. So I need you to do a little quick mental math. Okay, this we could actually do without any calculators. So let's just figure it out. I need to figure out how many moles and then ultimately how many what of this stuff to measure out. Grams. And I want, remember, most buffers are 1, 2, 1. So I got to figure out the number of moles. All right, so let's do it. So we got 20 milliliters. Always start with the quantity. Let's change that to liters. How many would that be, folks? There you go. Good. Times. Here's the easy part. It's what? 1 mole per liter. Well, that wasn't so hard. We're done. Okay. So 0.0200 moles. So that's of the acid. I want the conjugate base also to have that much. So now let's start with that. 0.0200 moles of conjugate base. Well, I'll just write it moles of NaCH3COO times. All right, and where am I going here? What are my labels? Don't worry about the numbers yet. Who's sort of following? I need to have what labels, Anthony? Yeah, where? Moles, no, not on top. No, Earl. Grams over moles. Remember, moles always got to cancel. So if I got moles here, I got to cancel it here. of the NaCH3COO. Okay, grams of it. You can figure out the molar mass, but the cool thing is it's always on the bottle. So I can just look it up, 82.0. And we can do that. So can you multiply that by 2? Double 82 would be what? 1. Well, we're at that decimal later. Do the numbers for me. 2 times 82, everybody. Okay, write it down. Now worry about the decimals, okay? So let's see, we got 82, okay? But now we got to go and move this over a couple, right? So it'd be like how many? Yeah, good, 80. 1.64 grams of this stuff. Good. And I measured that out already to save time. So here it is. I'll throw out my weigh paper in the weigh bucket. So now let's make up our buffer, and I forgot a string rod. Okay, so now I'm going to change these guys around. Good morning, Amina. Very much for participating. Hello, Bella. I'm going to change this so you can see some of this now, and I'll try to describe what's going on. Okay, so I put in the liquid or the solid in with the acid, and I'm going to just, and why is it so soluble? It's really soluble because what's it that's soluble? What did you learn? Na, no. Na what? Na plus. I'm sorry, there ain't no Na. In nature, there's not any Na anywhere. All right, it's Na plus. Don't get sloppy. Okay, so there's theoretically my buffer. We're going to check it in a second. But first, I thought, ooh, what if because we're almost out of this anyway, what if we're out of it? But I do have lots of 1 molar NaOH. So this is a typical AP problem and procedure that I want you to understand. So I'm not doing this for fun. I'm doing this as another way to like help you figure out how to make a buffer. Okay, I can also then take, let's write what's going on. Okay, if I've got 2 things now. So pretend that's gone. So I don't have any of my salt, but I do have these solutions. I've got the acid, the acetic acid, and I've got the NaOH. So now let's see what that would do. Let's turn our folks here so they can see now what's going on. Okay, well, if I got the acid, what's going to happen if I add some NaOH? What's the important part of that? What's the important? Enthalpy? Oh, wait, with what charge? OH minus. What am I going to get? And folks at home can guess too. So if I add H plus OH minus, what am I going to get? Good, a couple hands, but some same ones. How about some other ones? What am I going to get? All right, Aiden? Water. Yeah. Good, water. And then the important thing is what's left, Aiden? Thank you, good. So look at what Aiden has done. He's figured out another way to get the conjugate base. Remember what we did is we had the acid and then our base was the powder. Well, what you can do that's cool is convert some of your acid to base. Okay, follow with me. We're going to take 20 milliliters of this stuff and add 10 milliliters of this stuff. That means I'll be able to convert how much of the acid to the conjugate base. Essentially, how many milliliters will be converted? 10. So that means I'll have 10 of this left. So minus 10 converted equals 10 milliliters of the acid. That's gone, right? Because that's going to make the water that Aiden described. And then we're going to have 10 milliliters of my conjugate base. And look at what that means, gang. I got 10 and 10. I'm going to be making a hint-to-hint buffer. Isn't that cool? So even if you don't have the conjugate base powder, you can still convert half of it like we did here over. So for our notes, let's write convert some acid, some weak acid to the conjugate base. I'll abbreviate that CONG base. So that is tricky and cool and something you may need to know for the AP as well. Good. Thanks, everybody. Thanks for participating. I'm sorry I don't always see you, Mina, on there, but keep doing that. I'll try and look down. Okay. So let's do that too. Let's do that too. Okay, I used this one for my acid, so I'm going to use the same one for the acid now. And what did I say? I want to have 20 of my acid. My acid. Okay. And I'm going to add to that 10 of the, I'm going to add to that 10 of the NaOH. There's 1 molar NaOH. Good. Okay, I'm going to put it in another beaker just to mix it. Okay, there it is, but let's just mix it in here. Oh, it's warm. Why is it warm? What part of it is probably making heat? Can you guess? Making what stuff is making heat? Which product? Which product, Anthony? No. The water. The only one left, right? Water gives off heat when we make it because the bonds are very, very low energy, right? The two things you need to know with low energy bonds are water and CO2. That's why we have so many problems with CO2. It forms easily. So does water. That's why we have oceans full of it. And when it forms, it gives off heat because the bonds are such a low potential energy. Okay? All right, now, there's a slight difference in these buffers. What is it? Oh. True. On the other hand, we got water in the other two. It's a solution. It's just 1 molar solution. And here I had 1 molar of the 1 mole per liter of the solution, and here I had 1 mole per liter of the base.
Isn't there 30 milliliters or 20 milliliters water?
Ah, okay. So, well, 20 milliliters altogether. I got 20 milliliters of fluid, don't I? So, let's figure out what that does. Essentially, I got 10 milliliters of acid left, but now it's in twice the amount of fluid. So will it still be 1 molar acid? it'll be now what concentration? It's in twice the amount of fluid. Can we do it mentally, Lola? There you go. So now 0.5 molar acid. And the 10 milliliters of base is also sitting in 20 milliliters of fluid. So that'll also be 0.5 molar CH3 COO minus, okay, the conjugate base. This one's 1 molar and 1 molar. Does that really matter so much? Not so much for us, but it does mean that which acid will have more ability per milliliter, so to speak, or which buffer will have more ability per milliliter, Chelsea? The first one, it's got more, and that's your next lab, okay? It's buffer capacity. We talked briefly about last time. So if a buffer has more capacity, that does matter. But for our demo today, it really doesn't matter, okay? Questions before we now test our buffer? Yeah. Yeah, so we put them together in one beaker. And what we did is we put this with this. So we had 20 milliliters of the acid. We converted this in here. Is that right? Then I really screwed up. It's not 0.5. We got a bigger thing here. It's, let me think about this. So I started in 20 milliliters, and I've got 10 milliliters of acid left.
And then 10 milliliters is converted, which is the base, conjugate base, and 10 milliliters.
Right. But where's my error in thinking? Can you find it? Can you find it? Where's my error in thinking? Alessandra? Sorry, Alicia. Thank you. Okay, so thank you for finding that. So it's 30, isn't it? It's not 20, because I forgot. This 10 here, it's used up, but it doesn't like disappear. So I got 10 milliliters of base, and I got 10 milliliters of water, and I got 10 milliliters of acid, so 30 milliliters altogether. So what does that do? Okay, so instead of being 1 molar, yeah. So why? Because I have the same amount of moles in now 2/3 more fluid, so to speak. Okay. Again, that's not going to matter for us much, but at least you should know that. Why it has more fluid? Because I had 20 and I added 10. 10 plus 20 is 30. I just didn't think it through very well, Bella, until afterwards. So if I got 20 and I add 10, I get 30, and that 30 is composed of 10 still of the acid, 10 of the water, and 10 of the conjugate base. So 10 plus 10 plus 10 is 30, not 20. Okay, bad teacher. Okay, there we go. Let's test these suckers, okay? Now, I'm going to turn you guys so you can see the test tubes. What I did is I filled this side with distilled water, okay? And I filled this side with nothing. So let's fill it with the buffer. Now, for you and I, we're going to just add little bits of stuff, so it doesn't matter which one I use. They're both the same buffer. Just one is a little more concentrated than the other. So I'm going to use them both here. Let's see if I run out of this one. I probably will. All right, what's good I made then some of two kinds, because I don't really have enough here. And I want enough so everybody can see them. I'm going to hold them up too so everybody can see it, including the folks at home. Okay, all right. And there's my water. We'll try and put them at the same height. Okay, I'm going to add to my waters. Here's my waters. I'm gonna add to my waters universal indicator. Again, it's just something we use mainly in ninth grade, but it's gonna make it about what color for water?
Yellow.
About yellow. Okay, so let's go ahead and try that. So boom, boom. I'll do 2 drops in each one, so maybe we can get a dark enough color so everybody can see it pretty easily. Come on. Okay, and so, okay, so boom, boom, boom. Remember how did I teach you that? Use your thumb. Except I got so much frickin' fluid, it's probably not gonna do it, is it? Not very easily. Okay, well, let's start in the mix. Okay. 1, 2, here, will you guys help me out? Bang one of those with your thumb too. Just try to mix a little bit like this. Try not to have it shooting out the end. I do that once every blue moon, accidentally. Doesn't want to get to the bottom, does it? Yeah, that's pretty good. Okay, that's good enough. But we got most of it mixed, that's okay. How's the other one? That's not bad. Okay, all right. So we get an idea. Folks at home, they should all be fairly yellow. Here, let's put a paper behind that so they look sort of like their color. So that's a color we're talking about, okay? All right. Maybe I put too much in. It's hard to mix, isn't it? All right, okay. But it doesn't matter. We just got to see the color at the top. Okay, so I'm going to add, remember this is our water, this is our buffer, thank you. Okay, let's add NaOH to the first one, to the first water. Oh, wait a minute. I should add this to our buffer, shouldn't I? Okay, wait. Okay, so 2 drops of universal to each of the buffer, and let's see what the color is there. I don't really remember. 2, 2, 2, 1, 2. All right, we better mix those suckers too. Looks like it might be a little more on the end. What do you think? Now, if you want to grab one, just bump it a little bit. Excellent. Just bang it a little bit. So hold it. Yeah, you do that. You can also bang it with your thumb. That would be so kind of bang, 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 bang. I know it sounds silly, but it does sort of mix it up with it. You hold it tight and bang it with your thumb. I know it's like you're playing some weird instrument, but that's kind of how we do it. How we do it. So do you think this buffer is the same pH as the water? No, it's probably a little more on the side, acidic side. Good. And some buffers are. Some buffers are a little more acidic, some are really neutral, and some are a tiny bit basic. That just depends on what you choose, and we'll talk about that after we're done with our demo. Okay, you guys got somewhat mixed? That's pretty good. It's kind of orange, isn't it? Sure, yeah. Okay. Okay, there it is, gang, at home. So it's kind of orangey. There we go. So there's our color now of the buffer. Kind of see it. In a perfect world, these would be perfectly mixed. Okay, that's pretty good. Okay, so there's some colors for the folks at home. Buffer and water. Okay, so let's do the water first. So I'm going to add now a drop of NaOH. Okay, and it's 2 molar, so it's fairly strong NaOH. And the dropper doesn't work anymore. Well, that's not really very nice, is it? Good gosh. Did I use that? No. Can I get a drop out of here at all? Yeah, I can. All right. What's going to happen to the color? A drop of NaOH to my water. Blue, right. So universal indicator turns blue. Whoa. One slap, and it's already, look at that. Look at that. One freaking drop. Isn't that wild? One drop. That's all it took. There's my water. Folks at home, I hope you're impressed. Jumping up and down at home. Okay. Let's add a drop to the buffer. There. Okay. I'm just trying to get one to actually go down in the middle of it. All right. I'm going to mix that a little bit. Huh? Whoa. Any change? No. You know what I'm going to do? I'm going to go crazy. I'm going to like pour a little bit of this in here. I'm going to pour 1 or 2 milliliters of the NaOH onto this thing, into this beaker or this test tube, and see what happens to our buffer. I added, if you look here, an appreciable amount. Look at that compared to the other one. I added a bunch of NaOH. It didn't do squat. It's still the same color. Isn't that crazy? Anthony? No, it wasn't. Remember, it's acid and base. The buffer has both in it.
You added the base.
Yeah, exactly. So I can shift it. We're going to see again in symbols how this works. But essentially, I've got CH3COO minus. And these kind of go back and forth, don't they, depending on what I do. So if I add some NaOH, I'm making more what, folks? If I add NaOH, I'm making more base. So I'm going to make it like this. But that doesn't increase the amount of H plus or OH minus, so it doesn't really change the color. Now, the color might be slightly different, but not much, right? Check that out. That's really not much. You need some paper behind this. Yeah, that might be right too. Does it look any different as a shade, Lola? I don't know. It's still the same color, just a little diluted. You may be right. Okay. It does change a tiny bit, but not much to really change the pH. Okay, next up, we're going to add some. We're going to cover this up before I spill it. We're going to add some H2SO4, 2 molar. And is H2SO4 a strong or weak acid? Strong. That's one of the strong ones, isn't it? So I'm going to add a single drop of this stuff. Color should be of my indicator. Red. Here we go. Whoa. There's the one without. The one drop. One drop. Whoa. Crazy. Isn't that crazy? Look at that. There it is with, and there it is without. So it really, really matters. Okay. One drop to my buffer. Nothing. Let's put a bunch in. Let's put a couple milliliters of 2 molar, so it's strong, 2 molar H2SO4. Squirt, 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 squirt. Oops. Uh-oh, I might have gone beyond my what? I might have gone beyond my buffer capacity. That's so embarrassing. I'm sorry, students. Okay, here you think, oh, this guy didn't show me squat. All right, let's just do one. Let's just do 1 squirt. All right, so I did. I went too far. There's 1 squirt, which is really still kind of cool. I'll get the defect out of the way here. And you can see that it really isn't changing, even with lots and lots of drops of 2 molar H2SO4. Okay, you get the idea? Okay, so the buffer, man, stays being a buffer. There's the original. There's with the H2SO4. It's not really changed. And the water changes easily. With one drop, water changes its pH a great deal. It really matters. Ask creatures in the ocean about that. Okay, let's see if I've got any questions here or comments. Thank you for participating. Exactly. Righto. Yeah, good. Okay, let's point everybody back to the board for a sec, including my folks at home. So I've got this. And remember, can somebody find one of the, be right with you, somebody got one of the handy dandy buffer reactions? No, handy dandy buffer equations. One with like a fraction. Which one had a fraction in it? You got it? Here, Anthony?
Concentration of H plus
Good. Ka, and I missed the rest because there's kids out there. Good. Now I'm going to erase HB and put our acid. And I'm going to erase B minus and put our base, CH3COO minus. And so really, you can kind of see if I make the arrows go one way or the other way, then I'm just playing around with this. I'm playing around with this ratio just a bit. The Ka is still the same, and that really matters. And it's just multiplying and changing the ratio a little bit here and there. Okay? Now, you can tell from my mistake that I can go too far and go beyond the buffer capacity. And we may, if we get to our lab, we may be able to do that before the AP, before spring break. That's kind of my goal. Okie dokie. Good. Questions from folks at home? Questions from any of you? And Sophie? No. Because if I got a strong acid, I can't make it unstrong. I have to have a weak acid and a strong base. No, sorry. I got to have a weak acid and a conjugate base to make a buffer. If I got a strong acid, all it does is react with anything basic and neutralize it. And if I add more acid to it, anyway, strong acid just doesn't work. Absolutely. So Anne Sophia is a good question. What if I have this stuff? Remember, this was attached to any plus, right? Well, what if I only have a solution of that in the lab? Then I could add something to that to convert it to here. Can you guess what? So what could I add to CH3 OO minus? And it's not going to be very hard if you think about it to make HCH3COO. Add what? And Sophie? No, water won't do it. Water won't do it. Penelope. I got to add an H plus. Give me a good source of just getting H plus, you know, without like, give me a source that has that and then some bystander.
Water.
Water, no. Well, water, it's too much combined together, Errol. It won't fall apart easily. I need the H pluses really available. HCl, good, thank you. HCl. Yeah, I need a strong acid, for example, HCl. So, Anne Sophie, you bring up a good thing. So, I can convert my base to acid, and then I got some strong or some weak acid along with some maybe weak base that's left in a similar way that you and I added some NaOH over here to convert my acid to Conjugate base. Now I've said it. Good. And yeah, good source of H plus is any strong acid which you happen to have in the lab. Very good. Any other questions from any of you? Any of you? Okay, good. Then that's our buffer business. Before I forget, I'll try and grade a couple books if you have them at halftime. If I haven't graded your chapter 1 yet, I'd like to. If you brought your book today, please give it to me. But now let's break. Are we doing? We still got a few minutes. Let's break and see if you have some questions that we can answer in the book. Anything you're stuck on. So, questions from book. That goes for folks at home as well. And is this in your way? Kind of, yeah. I'll move that out of your way so folks here can see it. Good. Any suggestions? Page and or problem? Aiden?
Page 207.
Uh-huh. Number 1? Okay. So everybody flip to page 207. And number 1, this is about thermodynamics, chapter 3. What's the value for Gibbs free energy in the production of ammonia from nitrogen and hydrogen? So I got N2 plus 3H2 forms 2 NH3. These are all gases, so I'm not going to bother to put that. If the pressure of all 3 gases is 2 atmospheres, 2 atmospheres, we'll do sig figs later. And the temperature is 23 degrees C. Begin by getting delta G for the reaction using the reference tables from A8 in the appendix. So, okay. Remember, to get delta G, we got to take the G of the products minus the G of the reactants. Okay, that's just from the end of the book. To save me some time, does somebody have those values already that could read them all? What did somebody get for the delta G0 for the products minus the reactants for this one? Do you have them already?
I have the values for the.
That'd be great. Okay, so how about the value for the NH3 gas? Penelope. Good. So I want the number for the NH3. Negative 16.
Oh, yeah, negative 16.45.
0.45. Okay, so look at what's in, that's kilojoules per mole, probably, right? Is that the right label? Kilojoules per mole? Okay, thank you. Okay, so just trying to save time, Aiden. Don't take it personally. So I got 2 moles of that. She's got 2 that from the equation, and then minus, and then I'm going to put this in brackets, and I'll come back to Aiden. Did you find either one of these, the N2 gas or the H2 gas, the delta G values?
Well, it says N2 gas, the delta G is 0.
Delta G is 0 for N2 gas? Well, that's easy. What about the H2 gas?
H2 gas.
Also 0? Well, that's awfully nice. So essentially, you're telling me it's just twice this. So we can do that in our heads. So delta G0 is double 16.45, my people. Negative. Good. Now we're ready to actually do the problem. You got to get the original, Aiden, and then now we're going to adjust it because we got a different number of pressures and we got a different temperature. So the adjustment reaction is Watch, let me get some of this out of the way. So I can get a new delta G by doing what? What do I do? Somebody get me the reaction. What do I do? Penelope, you got it?
Well, you would do delta G plus RT.
Yeah, but isn't the delta G now 0, the original one? Okay, and then what then?
And then add RT. And then I'll Q.
Good, thank you. All right, so let's do it. Here we go. So we know this now, it's negative 32.90 kilojoules. Plus, I need from one of you the R in kilojoules. How about Alicia? What's the R in kilojoules? Good. Good. And then I need the temperature in Kelvin. It was 23, so change that to Kelvin. That would be how much, Penelope? Thank you. And now we're going to do this within the problem. You ready? Remember, Q is just the same as what other thing, essentially, Errol? What was Q? It's the same as what other thing? Two people know. I want everybody to know that. What is Q? It's the same as Penelope. It's going to be in partial pressure, but it's not the same as that. It's the same as what? K. It's the same thing as K. I'm saying that to you because I need all of you to think products over reactants. Okay, let's do it. So products, so it's going to be natural log of, and my products, look what I got. I got this in atmospheres, and we can do it that way. And I think, let me make sure there's no like liters or anything in this, in before I put those in. Yeah, so it's two moles, or 2 atmospheres, to the power, to the second, divided by 2 atmospheres. I guess that could be the N2 times. Beautiful. Okay, let's do a little math. Ready? Check this out. All right? Right? So really it just ends up being the natural log of what? 1 over 4. Okay, if you punch all that in, Aiden, I hope we get the right answer. Folks who had success on that, does that look like the way you did it? Okay, thank you. Let's see others. We're checking that. Good, we'll continue after our break. If you got a book to grade, hand it to me and I'll check it out. Thank you. Just set it there. Super. I'll get it in a sec. Okay. Okay, and I'm sorry. It looks like I lost somebody, but I don't know whoever random stuff is, and I don't know what you're asking. Okay.
On Thursday, next week is
Yeah, it's the whatever stuff. Yes,
and
it is Wednesday too. Wednesday, Thursday, Friday.
yeah, but on Thursday there's a mock AP exam, and
There's a mock AP exam for what?
for English, and it's from 9 to 12.
They didn't ask me if they could do that. All
And they
right.
said they asked the administration and the administration agreed to it.
Well, I didn't ask me.
Um,
Shit. I need that day. 9 to 12, huh? Okay, so when do I see you guys? That's Thursday or Wednesday?
it's Thursday. But
So
you see
I
us
see
at
you,
from like 12:15 till 20.
right, but you
Yeah,
guys
but
got
people
time to
going
get
home.
home too.
Yeah,
So let's change the time a bit, can we?
yeah, that's what I was asking.
Good. No, let's talk about that. What would be then a time when most folks would have time to get home? What do you
For
think?
me, it only takes me like 15 to 20
Yeah,
minutes.
let's say it
to get
takes
home.
some, I don't know, 45 minutes. Something.
So then like 12:50 or so.
Yeah.
Why don't we start at 1? Could we do that?
Yeah.
Okay, let me write this down. So it'd be next Thursday.
At 1 until, are we going until 3 or 2?
How about 1 until 2:30? All right. Does that sound okay?
Yeah.
Okay, so that'll be next
And only our AP classes are the ones continuing.
Thursday. Yeah, exactly.
But not all like English. He doesn't care.
Mr. Weiss, may I take a picture of the buffer thing?
Please take all the pictures you wish.
Also, can you take a picture of our English chemistry class?
Okay,
Taking online school on Wednesday or?
yes,
Okay, so Wednesday is the day it starts.
exactly. So I'll do a regular live stream from my basement on Wednesday.
And it's only the EP class?
As far as I know, but I don't think they sent me that information, Errol. So you guys may know more than I do. Okay. Good. Good. Okay. Okay. Errol, that was easy. 30 out of 30. That's good. That's the way I like it. Quick. Everything done. Thank you, sir. Okay. Okay. Well, sorry, Will, don't take it personally, but I just hid all of your text messages. So, adios, muchacho. Okay, so let's put some of these things back. Put all this back.
Your book. Random stuff. I'm really
Hey, yearbook. Ellie, are you yearbook? Do you want an eighth grade yearbook?
Yeah. From this year?
Well, from 2020. You didn't go over it.
No, yeah. Oh.
No, wait, when did we go?
No,
Yeah. 2020. 2021, we're not going.
okay.
So
It
we're
would be great if we came this year.
Did they also end that one early?
Yeah, my brother was on that
After a
one.
week, we came home.
I was super excited to have 2 weeks without my brother, and then he came home. I was like, no. It was so bad. Oh. And I think that's it.
Hey, Aunt Sophie. Okay, you're welcome.
Oh. Oh, yeah. I mean, I don't know, it's very clear. But it was, also, the I don't know, it's very short. I didn't go in.
Wait, can I ask Mr. Wise one question? Yeah.
What things do we do for calculus? I don't know, maybe you should calculus, we only have like 11 pages right now, and it's like taking to the. You can take a picture of your name, writing an equation, or, you know.
Yeah, so that's why I was gonna ask Mr. Wise. And when everybody comes back, like, the different
What? Oh, right, oh. But that's the graph mathematical.
like, classes, is like, it's cool, and it's only like 11 or 12 years that are back. And then like go out of the
Alright, so,
So then, can we take a picture of the class?
if we got everybody's permission.
Guys, is it okay if we take a picture of the class? Please put in your book.
Are you in charge of your book?
Yeah.
Did you?
Ask specifically if you got your photo.
Yeah.
Okay,
I'm not in charge of the data, but
look
looking at
natural.
Was it okay if there's like
I mean, it's a picture of everything, I think it's we're gonna do what are we supposed to do? Are we supposed to? I think act natural. Act natural?
Do something chemical.
Oh.
To act natural, physically naturally. Ignore the camera. Yeah, that's great. Thank you.
Okay, very good. Let's talk about another thing with buffers, and that is how to make a buffer for an exact pH that you want. And I think we didn't get this far last time. So let's say we want to make a pH of a buffer with how to make a buffer with pH equal to 9.00. Well, first thing you got to do is pick something close. So can I find this briefly? Maybe somebody can help me. Yeah, there. Okay, so. All right, everybody turn to page 277. I'll show you where I'm looking. It's all the Ka values for the acids, page 277. I want then a Ka value. Okay, remind me this, okay, gang? If it's actually a pH of 9, then what does that mean? The H plus concentration is exactly what number? Remember how that works? If it's on the money like that, then the H plus is what number as a concentration? I'll give you a hint. 1 times. Ooh, you got to be able to go backwards quickly. Penelope? No, that would be water. That would be water. Easier than that, Penelope. It would be, Chelsea, -9. So all you do is if the front number is 1, okay, then that's the exact number here. Or to say, if the front pH is just a regular whole number, then it's 1 times 10 to the whatever molar. And remember the formula I got earlier from Penelope or somebody, it was the K, it was Okay, I'll just write it, Jesus, okay. So it was this, right? Times concentration of HB over B minus, right? But you know what? If it's 1 to 1, then really, what's the deal? The H plus is going to equal the. Now you see where I'm going. Can you look on the KAs on page 277? Find one that has 10 to the negative 9th. Are there any that have 10? H2BO3, but that one is so bizarre. I don't even know where to get boric acid. Oh, look at that one. Let's pick that one. So see the one that has NH4 plus and NH3? We're going to take that. Folks at home, see that? NH4 plus, and see it's page 277. Page 270. They took a picture for the yearbook. Don't worry about it. You're there in spirit. Okay, so we're going to use, to do this, remember we're trying to get a pH of 9 with our buffer. We're going to use that pair. So use NH4 plus, and this pair, there's the base, NH3. And the Ka is, what, 5.6? Okay, so let's do it. Where did my paper go? Here it is. So that means the question is, how much NH4 plus, how much NH3? We need to know how much of each. And we don't want 1 to 1, right? Because if we did that, it would be this pH or this H plus concentration. That's not exact 9. Okay? So we got to tweak it a bit. So here's what you do. All right? This is kind of cool. I want to get the H plus divided by the Ka now. Okay, I'm just going to divide that over. And that's going to equal my ratio of HB to B minus. You might say, well, Mr. How can I do that? It's just that equation. Solve for this ratio. This ratio is what you want, okay? You'll see why. It ends up being easy. Now, put in the numbers. You ready? So we're going to put in, we want the pH of 9. So that's 1.0 times 10 to the negative 9 divided by the Ka, 5.6 times 10 to the negative 10. You might say there's 2 variables. Oh, don't worry. Can you divide these and let me know what you get? Okay, what do you get for that division? Looks like something more than 1.
1.8.
1.8? Others get the same? Good, thanks for checking. Now, here's the cool thing. You ready? Watch this. I can put it over 1. In other words, think of how powerful that is. So if I have 1.8 moles of of HB, but we know what HB is. Now it's not, here I should erase this. For us, it's NH4 plus. And my base is not B minus, it's NH3. Sorry about that. So I need 1.8 moles of NH4 plus and 1 mole of, who's sort of following what I'm talking? 1 mole of entropy, NH3. Isn't that cool? So you know how to make that you've tweaked it. Instead of being 1 to 1, it's 1.8 to 1. And that makes it exactly a buffer of 9 instead of whatever it was originally if I had 1 to 1 for this particular set of chemicals. That's pretty cool. So I could do that, or I could do 9 moles NH4 plus and 5 moles NH3. What did I do? I just multiplied it by something, right? So I multiplied it by 5, right? 5 times that, 5 times that. In other words, I can do any multiple of that. It will still give me the nice same buffer. Or I could multiply by 0.1 each number, whatever. You know what I'm saying? And then you go to your lab and start to measure out that amount of grams to get those amount of moles of each one, like you did today.
When you do the division of the numbers,
Yeah.
will it automatically, like the 100% become the NH4 plus, or could it also become the base, and then the ratio stay the same with 1/8?
That's a good question. You're going to get a number, and whatever number is, that goes on top, and that'll be the acid Lola. And then on the bottom, every time you could just put a 1.
Okay.
Let's say it came out to be less than 1. Let's say it was like 0.7. It doesn't matter. Then it'd be 0.7 to 1. But it will always be the top number. That's a good question. Mathematically, that's how it works out. Exactly. Okay, good. All right. Make sure everybody can see they're at home. Would this make a buffer? I got 0.20 moles of NH3. And I add 0.10 moles of HCl. So yes, no, and why? Okay, would this make a buffer? Write it, and I'm going to have everybody think about it when you're walking around the room while you're thinking. All right, how many say no buffer? Okay, how many say buffer? I got 3 people voted out of 9. That's not so many. Should we try a vote again? There's a buffer or not? How many say no buffer? How many say buffer? Oh, it's even less. What about you at home? Can anybody say, yep, buffer? Buffer, no buffer? I wish I could see. I'd have you do a thumbs up or a thumbs down. So just write in, buffer or no buffer. You should be able to know the answer to this because we already did this earlier last hour. think of the buffer system we were just using. NH4 plus and NH3. Shall I help you out? Here, watch.
It's not the conjugate acid or base to the acid.
Also,
Isn't it a strong acid?
Yeah, that's a strong acid.
Oh, I mean, the buffer was a strong acid.
That's a B.
No buffer, any buffer with a strong acid.
Lola.
I think it can make a buffer because you're adding less of the HCl, so the HCl will add an hydrogen ion to the, will add an H plus to the NH3.
You better believe it's a buffer. Yeah. So for exactly that reason. Now, we talked about that last period, and now I've done it a second time. I want you to be able to recognize that because every single year, that's some kind of multiple choice question on the AP. You've got to recognize that if I convert, like Lola's done in her head, some of the base to acid, then I've done it. Let's add the numbers. So I got 0.2 moles of this stuff. I use up all of the 0.1 moles of this stuff, and I make then 0.1 moles of this stuff. Oops. And I got 0.1 moles of this stuff left. You see what I'm saying, gang? So you've converted half of your NH3 to NH4 plus. And now I got a hint-to-hint buffer. One-to-one buffer. That's important. And that's definitely like the definition of a buffer, okay? Well, it doesn't have to be one-to-one, but it should be pretty close. Yes, yes? Folks at home, questions? Did anybody guess? Yes, buffer was right. Yeah, Bella. Okay. All right, so. Ute. You know what? I'm going to just skip that, I think, this year. Let me go through and just, so essentially, everybody, I'm in chapter 6. I'm not doing it in the same order as Cheryl, but some of the stuff you and I have done together anyway. The salts, the acidic and basic salts, we already did. That's 6.1. 6.2 is about buffers, and that's what we're doing now. And life is beautiful. She uses the same buffer equations as we do, so we don't have to buff up on any new equations. Capacity, if we get to that, we swell. Nope, we're going to skip it this year. Go to titrations. What I'm doing is I'm seeing if she talks about indicators in a way that you have to know chemically. Frickin' A, she does. Damn it. Okay, I better do it. Okay. All right, here we go. Okay, now, we're going to talk about, and it's another lab, I don't know if we'll have time to do it or not, maybe we'll have to do it in April, but it's about titrations. Titrations are adding an acid to a base or a base to an acid. We talked early in the year about doing this. But now let's talk about indicators. Okay. We had, it could be louder, but I'm not sure how. We have universal indicator. And that's the main one I use in like ninth grade, if you had me then. Why is it not really so useful, can you guess, for doing actual chemistry? It's fun to see, but
It tells you the region of the pH, it doesn't give you the exact.
okay, you're on the right track. So I don't get an exact pH at an exact moment. Like it gives you a range, but it doesn't really give you one color change. And here's why. Universal indicator, it's a mixture of like 2 or 3 indicator chemicals put together. Not helpful, but fun. So it's fun. What we need is kind of like what Anne Sophie said, we need an indicator with an exact pH when it changes color. Let's make it clear. We need indicators that change color at an exact pH. And now,
When I had this challenge in my class, we used like paper.
yeah, you use, and essentially the paper thing, the pH paper is more or less the same solution, universal indicator solution. So it's also fun, but it's not really terribly useful for a lot of stuff. Okay, so how do these work? I want to talk about indicator chemistry a little bit. Okay. Acid-base indicators. And by the way, this period, I know I kind of cut you off. I'll take more of your questions tomorrow. Okay, but I want to get through some material in the time we have, which is, okay. These are derived. These are derived indicators from weak acids. That means we're going to treat them like that. Okay, here we go. We're going to call it H indicator for the acid part, and it's going to go to H plus indicator minus. In other words, they've got the same parts as a weak acid and its conjugate base. They got an H indicator and an indicator minus some sort of negative ion, just like we had when we had HCH3OO and we had CH3COO minus. So it's just kind of like that idea. Like we did up above with that ratio, the ratio of the acid, H indicator, divided by the conjugate base, indicator minus, shows what color you get. Let's see why that is. So here's the scoop. It's all about this ratio, okay? If the ratio is greater than like 10, you get the color of the which chemical is on top, so to speak, in your ratio. The color, Anthony? of the HIN, of the acid. So you get the acid color. And if the ratio is less than 0.1, then you get like the bottom color, so you get the base, the conjugate base color. And if it's pretty close to 1, the ratio, you get a neutral color. Now, I'm going to put that in parentheses because, to be honest, folks, the way most of these work, these indicators, are you get one color for the acid side, one for the base side, and that is it. You don't get like 3 colors, you just get 2. Now, entropy. No, that's the point. There's not a neutral color. It's like I got this color or this. Generally, there's not a separate color for neutral.
So if it's neutral, or if it's like about 1, would it just stay the same color?
Yeah, it'll be either the color of the acid side or the base side. You don't get an extra color. In other words, if you were phenolphthalein, which we'll use if we have time to do a lab, you're going to be either clear or pink, or anywhere in between. And if you're neutral, that's still going to be on the pink side. So you won't see a color change until you get to the exact special pH where something changes. So really, two colors for indicators. Now, I'm going to vote out the end point that's the moment the indicator changes color. The equivalence point, that's the point where you've got an equal number. Well, let's put it the point where the reaction is complete. That usually means an equal number of moles of acid and base. Okay. Now the trick is pick your indicator so its endpoint matches the equivalence point. You're not going to understand that totally, but please do write it down because we're going to talk in detail about it in the next hours. So they sound like really similar things. Ideally, they're the same moment. But if you don't pick your right indicator, they're not at the same moment and you're screwing up. So we'll see how to pick the good indicator based on the endpoint that matches whatever chemicals you're titrating. So this is all about doing good chemistry. Turns out there's about 20 indicators. We're going to have to really only learn 3. And we'll kind of talk about those 3 as we do our process of learning about titration now Now that we got indicators kind of out of the way. Anthony. It's sort of, not necessarily, Anthony. It's sort of like this. Here's my indicator. It's going to change here. Or I could pick another indicator that changes. Oh, sorry. It's a sponge. Okay. What you doing? Hold on, a sponge. Okay, here's the indicator. Here's the reaction. Okay, let's say this is the point where I have equal moles of acid and base, all right? So I can pick an indicator that kind of changes here, here, or here. Well, obviously, I want to have one that changes right here. At the same moment that this changes, I want the indicator to change. But some indicators change earlier in the acid side, and some change more later in the base side. You might say, well, that's kind of stupid. Well, it only is because we haven't learned yet when the whole thing is shifted to the base side, or Anthony, shifted to the acid side. So the three indicators we'll learn, one is for the acid side, one's for the middle, and one's for the base side. Okay? That's where we're headed. And those are the three cases we need to know about. Okay, oops, sorry about that. I should have showed you the sponge too, but anyway, it's not so important. Okay, then let's talk about the first case. The first case of titration. And this is more or less what you might have done in another class. It's a strong acid with a strong base. So titration is adding acid to base or base to acid. Case one. Strong acid, strong base. Case one is the easiest case, and it's kind of what we've done a little bit already. So case one will be a little review for you in many ways. Basically, if I got a strong acid, gang, the only thing important here, I'll ask you guys too. If I got a strong acid, the only thing important out of the strong acid is the what? What's the important thing out of the strong acid? Arrow? H plus. If I got a strong base, what's the important thing coming out of the strong base, Penelope? OH minus. You see what I'm saying? So this is relatively easy. I don't have to worry about the spectator from the strong acid or the strong base because I don't care. And of course, what they make is H2O. And remember, why does this work so well? Because the K for this is 1 times 10 to the 14th. It's huge. So it works really well. Remember, for water to fall apart, it's 1 times 10 to the negative 14th. To the negative 14th. But to make water, it's 1 times 10 to the positive 14th. It forms easily. Okie dokie. So let's talk about let's talk about a graph. On a graph, we're going to talk about, this is the pH on this side, and this is going to be the milliliters. Give me a classic, how should I do it? Give me a classic strong base. Strong base that you've learned this year. NaOH, thank you for analysis. So milliliters of NaOH added, let's say 2 HCl, because we all know that's a strong acid. Well, if I just start with none, 0 milliliters, I'm probably going to start at a higher low pH. Ellie, what do you think? I'm adding NaOH, but right now I've added none of it. So I just got my bowl of acid. Low pH. So I'm going to start at a low pH. So we're just going to draw that. And now I start adding some, so the pH starts to go up with low, high. Here's the thing, it's not really linear. What happens is, after a little bit, it starts to go like this, and I get a really big change in a short period of time, and then it goes like this. So it has a lot to do with calculus. And this point in the middle, do you remember anybody what that is in calculus, if you've had it? It's called the inflection point. Inflection point. You don't have to know that, I'm just telling you. You'll see it again in calculus. Well, that's the point in chemistry. If I got a strong acid and a strong base, where I hit what pH? Can you guess? Ellie? Neutral, which would be what number? 7. Exactly. And notice how steep the graph is on one side or the other. The pH really changes quickly when I'm getting close to this spot. And that neutral spot here in this graph is the equivalence point. So if you were supposed to find the equivalence point, that's it right there. But I want you to sort of realize, whoa, quick change, quick pH change. Oh, not quick. Rapid? Okay, I'll write rapid. Rapid pH change before, I'll just say close to the equivalence point. And I'm going to abbreviate equivalence point, EQ point, because we're going to use it so often. But that is important. Why? Because the other graphs we look at aren't going to look like this. This is a classic strong graph, okay? So it's real quick change from acid, or a steep change from acid to base. Ute. Okay. Doing all right? We're doing all right. Okay, we're going to do an acid-base titration in just a second, but I better stop and tell you about our 3 indicators that you need to know. Okay, so here's a little aside. The 3 indicators we need to know are these 3. One is called methyl red, and NR is its abbreviation. The endpoint is like between 5 and 6. So it changes its color more on the acidic part, what I was talking to Antonine about earlier. The next one is bromophenol blue. And that's going to be BB as an abbreviation. And this changes at a pH of 7. So it changes right like where we're used to it happening, like in 9th grade. And the last one is the one that's fun to say, phenolphthalein, which is PP. And that sucker changes between like 9 and 10. So that's going to change more on the basic side of things. And again, I know you're wondering why it doesn't always change at 7. We're going to find that out in the next couple of class periods. Yeah.
What do you say the second one?
Okay. So why don't you say all three with me? Here we go. Methyl red. Are we doing that all? Bromethymol blue. And the fun one, phenolphthalein. That's pretty good for the first time. Okay, we're gonna if we get a lab in, well, 2 labs in, if we get our second lab in titration, then we'll use phenolphthalein. So you'll have lots of practice saying phenolphthalein all day long. Okay, yeah, all right. Okay, let's start at least our example, and we'll see how far we get with this today. Okay, so example. This is again strong. 50.0 milliliters of 1.00 molar HCl is titrated with 1.00 NaOH. Find the pH when A, no NaOH is added. In other words, let's find the pH before we begin. Okay, so we need to find out what would be the pH of the 1 molar HCl. Okay, you might be able to guess it, but let's go ahead and do it. Remember, pH, we're after the pH in each of these. So pH is negative log of the, thank you, Chelsea. So just put in 1. It's 1 molar and find out what happens. Maybe you know this already from math, I don't know. So punch it out, see what we get. It's a B.
Is that supposed to be 1.00 molar?
Yep. Yeah, they're both 1.00 molar, the HCl and the NaOH. Okay, and what'd you get? No. 0. Weird, huh? So we're starting out at a really low pH. I think I told you pH can be even below 0. It's even stronger than that. Like 2 molar HCl would be some negative number. So it doesn't start like 1 to 14 like you might have learned from some bad teacher in 9th grade. Okay, never mind. Don't get me started. Here we go. Let's now do something more interesting. Let's do B. So A is kind of like, okay. Okay, so we have 50 of the acid. So B is we're going to add what? If I got to get the right sheet of paper here. Okay, we're going to add 49.99 milliliters of NaOH. Now, let's just see what's going on, okay? Kind of like, remember how we did this before when we were adding some of the, like a conjugate acid, changing it to the base? We're going to do the same sort of thing here. I got what? I got how much acid, folks? 50. So here we go, 50.00 HCl milliliters minus, because we're going to neutralize this much, right? It's going to become water and stuff like that. Before you go, let's just crank this out. It's going to mean what? What number is physically left? How many milliliters of what? Good. And we'll finish that up tomorrow. But we got a good start.
So the other 99.99 will use water.
Yep, water and a salt. That's right. And neither of those, because it's strong, neither of those will affect the pH. Good. Okay, folks. Thank you. Happy St. Patrick's Day. Think some green thoughts out there. Bye, everybody.